My name is Anuj, and I'll be your instructor today with the topic of logistic regression using Python. So today we'll talk about data science in general. We'll discuss about the life cycle of a data science project, which is very important and fundamental to know. Then we'll talk about different type of model. We'll then jump into the regression, what it means, and why do we need regression. Then we talk about the specific model, which is the focus for today's discussion, logistic regression. Then we'll do a little comparison between regression, linear regression versus logistic regression. How do we call it logistic regression, so on and so forth. And we'll also do a quick demo on Python. And I'll talk about how much depth we are going to get into when we do the hands-on session. So with that, let us start. What is data science? This being a very old and very popular domain, specifically in today's world, there have been a lot of definitions and explanation on what this actually means, right? There have been some abstract definitions, abstract explanations. Then there are some interesting and funny or lighter ways of expressing this. And then we have the detailed explanations on what data science is. So for example, somebody very famous economic Nobel Prize winner, Ronald Coase, said that you can torture the data enough to confess anything. So at a lighter note, that's how I was saying people try to define this. However, from the business perspective and the practical scenario, when we apply some scientific methods, which are a blend of mathematics, statistics, and some other technical expertise, including tools which can be either programming or visualization or big data tools, etc. And when we cap all of this with business domain expertise, we say we are using scientific methods. Now, when we apply this to solve a business problem or answer a business question, where we are utilizing historic data, we call this the domain of data science. So as a more educated and nice definition, we can say it is the process of extracting knowledge and insights from data by using these scientific methods. With the evolution of this domain, there have been a lot of changes in the name, and sometimes we loosely use a lot of terms. We use different terms interchangeably. And for people who are new in this domain or getting trained or are aspiring to get into this domain, often ask these questions that what is the difference between business analytics and data science, or what is artificial intelligence, machine learning, how is it related to data science? So in the industry, as I said, people generally use a lot of terms interchangeably. However, there are significant differences in these. At a very high level, data science is more holistic domain definition, where we have expertise on both technical as well as business domain expertise. And business analytics somewhere falls under as a subset of data science. And artificial intelligence and machine learning, any which way, are part of data science, so they are subset of data science, right? For more information and details, you can always check our Edureka's pages on different websites to attend these kind of webinars where we only talk about these specific topics. But I thought I'll give you some background. So when we talk about this domain where we are trying to solve business problems or answering to business questions which are important, we follow a life cycle, right? Which means there are specific guidelines or stages which we have to follow when we are implementing a data science solution, which we call as life cycle of a data science project. Now, this is one of the ways to define the life cycle. So we have business requirements as our first block. So data science projects start in either of two ways. One is we already have a problem or a question to answer from the business perspective. They might be struggling for something, they want to predict something, they want to make some decision, things like those, right? So they already know what they are looking for in terms of answers. Or sometimes there is a lot of data for multiple reasons. They have collected a lot of data because there are a lot of systems and data is flowing into the organization. They are running processes and things like those. And then we also know that there are a lot of insights and hidden gold in the data, right? So sometimes we also say, okay, let us pick this data and see what we can do with this. Can we find some patterns? Can it help us in any way? So we don't have a specific business problem or a question, but we are just trying to dive into data, and then we want to get some insight. So these are the two ways typically a data science project would start. However, mostly the first method or first way of asking a question or starting with a problem is the primary reason to start a data science project. So once we are there, we do data acquisition. We have to collect data for sure. Once we know what we are trying to solve, then we process that data. And processing, we have a lot of pre-processing, and the crux is that we need to ready the data for entering it into a data science model like logistic regression. Right? Every model has different reason to be used and different ways the data can be fed into this. So we have to take care of all that, and we'll talk about this in a while. Then we explore the data, which means we are trying to do some understanding of the data. We go through the data properly. We try to visualize the data in different formats and perspectives so that we get some high-level insights where we start to understand that which direction we need to move into, or we can build hypotheses around the exploration of data. Once that is done, we have the data ready. We know what we are trying to solve for. We also have explored the data where we know what the data is telling us at a high level. So we put this data into a model. We train a model and see what the model is telling us, whether it's a hypothesis-based model. So is it rejecting or failing to reject the hypothesis, or is it predicting something which we need? Things like those. So based on that, we get some output, and then we try to do any of the analysis, which can be descriptive, things like those. And finally, once we are good with our modeling and we are pretty comfortable with the accuracy, etc., which have been achieved, we deploy this model in production, which means once the model is trained and we are comfortable, we are going to give it the live data on which we really want to predict things, or on which we want to answer the questions of the business. And this does not end here. It's always an ongoing process. Once we deploy, we then monitor the model, and we fortunately continue to get more data on which we are making predictions. And then we continue to test how the prediction match with the real output. And then we fine tune the model, and we keep on doing this. So, we can then add a few more business requirements, etc. This kind of cycle will continue to implement, continue to run. And that's why it is, obviously the name life cycle. It's a cycle. It's not never ending process. So as you have seen in a life cycle, we have the first was business requirements. So business will come to you and they will explain that they are facing this problem, or they want answer to a specific question. And now your job as an analyst or a data scientist is to convert this business problem into analytical problem. And here you have to be very careful in terms of completely understanding this. A very basic example, business tells you that we need to implement a very basic solution where we want to. So this is a credit card company, for example, a very typical example, very common example, but it's a good example. So a credit card company tells you that we only want to issue credit cards to good customers. Now this is the business statement. Now as a data scientist, you have two approaches. One, you assume what are they talking about. They are saying good customer. So what is a good customer here? Or you can ask. When I discuss this with a lot of students, so people give different answers to what a good customer can be. Somebody would say, okay, good customer is who pays on time. Somebody would say who doesn't default, and things like those. But then if you look at it more deeply, you will know that the business might tell you that right now we are going through a cash deficit. We need cash. So for us, good customers are those who pay on time. Or in a different scenario, the same business can tell you that good customers are those who pay late, because we don't have problems of cash right now, but we want to earn money. So whoever pays late gives us a lot of interest, and that's how we make money. So good customers for us is somebody who pays but pays late. And of course, it's never a default customer, right? So that's where you have to be very careful with each and every word in a business problem. And then your job is to convert into an analytical problem so that you can solve this. Once you have business problem converted into data science problem or analytics problem, then your job is to understand what all data you need, and then you collect this data. Here we don't need data science tools. This all depends on the source systems, and it can be a CRM, ERP, external websites, or your competitors' information, or you have to buy some data outside. You can have primary research and things like that. So there can be any source system through which you have to collect your data. Now comes the interesting part, which is data processing, and it kind of means you have to pre-process the data, which comprises of cleaning it, standardizing it, and doing a lot of other things. Objective is, as I told you, you have to build your data in a format which you can feed into the model that you are going to implement. Now, one interesting thing is, even though you have read different articles and things like those, 70 to 75% or sometimes even more time goes into these steps like data acquisition and data processing. It's not the most interesting thing to do in this whole life cycle. However, this is the most important thing. You would be spending a lot of time here just because the way the data has been stored and it's being collected from different sources. So just be ready for it. Now here what we do is we standardize the data. We kind of, for example, it can be in different currencies, different time zones and whatnot. You have to bring everything into a standard format. Then the problem of missing values or incorrect values because the data has been captured manually or by using tools, and you have to make sure that you use statistical methods and very intelligent contextual based techniques to do all that. Sometimes you have to delete the data, you have to identify outliers, you need to understand how do you treat the outliers, because in analytics and data science there is no standard rule. That's why people are highly paid, because it uses a lot of intelligence and it is always context based. It's very interesting to know that if you give the same business problem and same data to two different data scientists, they will come up with different results because they are using their own techniques, etc. And that's what makes this domain the most interesting domain in related fields. Once we are done with data processing, we are ready with the data in the right format that we need. We do data exploration, which means we now are visualizing this data. We are trying to retrieve high-level useful information. We are trying to form hypotheses. When you visualize, you kind of get the high-level patterns, and it'll help you to know which direction you have to move in. What all fields are important, what are the fluctuation in the data based on specific fields, tenure, time, and things like those. So as it is said, a picture is worth 1,000 words. In data science, it's a million. So you always have to spend a lot of time in exploration and visualizing your data. Then it's about modeling. So let me first tell you what a model is. There are three different types of models or algorithms which are used in data science to solve a problem. One are statistical models, which are based on statistics, mathematics, and they use structured data. And structured is a standard term here in data science, which means tabular data. Okay, unstructured is anything which is non-tabular, like text, video, audio. Those are unstructured. Even though there is no unstructured data in reality, but in data science we have structured data and unstructured data. So structured means tabular, unstructured means non-tabular. So when we are talking about statistical models, we are talking about the algorithms or programs or models which are built based on statistics and mathematics. Then we have bio-inspired models, which are based on biological objects in this world. A typical example or a most widely used algorithm is artificial neural network, which tries to replicate how human brain works. So it is bio-inspired model, right? The scientists have observed very interesting patterns in how brain works, and they have tried to replicate that using computers. And this is where we have and we have different other models as well. So these are bio-inspired. Finally, we have a set of models which are nature-inspired, which can be a cuckoo search algorithm. So we know the bird cuckoo never lays eggs in it, like it never creates or build its own nest. It always lays eggs in some other bird's nest. However, it has a natural instinct to calculate the probability of maximizing the hatching of the egg, so that the eggs are hatched. So scientists and academicians observe this natural phenomenon, and they try to replicate this using models in data science. Then there are algorithms like frog leap. So when frog basically has to go from one place to another, it leaps and it jumps. So how does it know where to land or where to how fast it should leap and things like those? This natural phenomenon is also captured, and these, for example, the first one, the cuckoo search, is used by the cab service providers like Ola and Uber for some of their applications. They use it widely. So anyway, so these are three set of algorithms and models. Now our logistic regression and linear regression, which we are going to talk about, fall into the statistical subset. Now when we say modeling, we have certain fixed kind of guidelines, not rules. We first of all look at what we are trying to do. Is it supervised, unsupervised, or reinforcement learning? Are we doing regression or clustering or classification? Then we kind of have a filtered set of algorithms. So it can be like 50 algorithms available for, say, classification, which I want to do. But how do I choose those 50? I can't run 50 algorithms to test, because in the real world, sometimes you run an algorithm which will run for days, if not for long hours. No, you can't do this for, say, 50 algorithms. So what you do is, based on your experience and learnings and guidelines, you look at the data, and then, as I mentioned it earlier, that every model has a different set of expectations, performance, and the kind of data we feed into. So looking at the context and the data, we can intuitively tell that these models will do well on this kind of data and this kind of problem. So we pick four or five models. Typically, we run all of them, and then we do a lot of comparative analytics like those. We check the efficiency and a lot of other things, which we'll talk about when we do the hands-on today. So that's how you do modeling, and you get the output. And then it is another most important step, where now how do you interpret and convert this information into a business solution. So far, you have got a technical or a data science solution. Now you convert this into a business solution, and that's where today in the industry we face the biggest problem, where we don't have good storytellers. We have very brilliant data scientists who can they can have efficient programs and whatnot. But when it comes to storytelling, because business doesn't care about which model you have used or what techniques you have done, they only need to know what is the solution, and if it is not in the business language, it doesn't make an impact, right? And you have to then help in prescription, what needs to be done to achieve something which they are trying to do. So always remember, when you're getting into this domain, you have to be very good storytellers. You have to spend a lot of time in learning visualization. Then eventually you deploy, and in deployment there are multiple teams involved. But the idea is that you take your model to production, you get real data, and then you capture this real time or near real time, and you give the solutions to your business users and decision makers who can utilize what you have done. So that's the life cycle. So what is a regression? As I told you, we can do only two things in data science at a high level. One is either we do regression or we do classification. Regression means we are trying to predict a point value, how much sales will happen, what will be my attrition in the company, when will COVID will come, like it can be a time series regression, things like those. But when you're trying to predict a value, it can be time, money, or any point continuous value, you are talking about regression. Whenever you're trying to put objects into groups, like your data into groups, different groups or classes, we are talking about classification. Classification has more legs, like it has a classification itself, and we have clustering, there can be association mining and things like those, which is a different discussion altogether. But for regression, we have so it is all about finding relationships between your independent variables and the dependent variable, which is also target, for which you are trying to predict something. Now, it can be as simple as a simple linear regression, where typically there is only one target and one predictor. So predictor, as you are seeing, is the independent variable, right? Based on which we are trying to predict something. When we try to graphically explain this, and the idea is, because graphically we are able to understand better, we are talking about a simple linear regression. Typically, what we try to do is, initially we try to explain things visually and graphically, because it makes more sense. Now here we are trying to explain what is linear regression, and we are only taking two variables. One is your X variable, which is your independent variable, and then you have your predictor, which is on the y-axis. And typically we take this standard nomenclature, where we say y is always the dependent variable and x can be set of your independent variable. So here the set contains only one variable, right? So here we are saying there is some values ranging from say around 5.6 to 6.75 in terms of x values, and based on this we have some y values which are ranging from 108 till say 120. So what we are trying to do here is, we are seeing or trying to find a relationship between x and y, so that when we get a x which does not already exist in our data, we can try to predict. Now there are multiple ways to do this. One very commonly used way is OLS, which is ordinary least square method, which is being used in this graph. So we are trying to represent the whole data with a straight line, where we have the straight line equation, which you have studied in mathematics, primary in 10th, 11th school mathematics, that you have y is equal to mx plus c is the equation of a line. That is kind of a representation, and we try to put a line which crosses closest to from all the points, and that's where we say we are trying to reduce the error, which is ordinary least square. And there are, in itself is a very vast model to understand, but as a generic understanding before we move to logistic, it is about predicting a point value based on your input values, based on equation of a line which has been devised so that this line crosses nearest to all the points, minimizing the errors. And error is nothing but the difference between the point on this line versus the actual value. For example, if I look at the value, say 5.90, the actual value for this is beyond or above 112, right? So if you see this point, I'm talking about this one. So here I have a value around 5.85 or 9, and here it is around 1.13, right? However, the predicted value which we have is on this line. So this is an error. Now we draw this line to have this error minimized, and there are, that's where we use the line equation of a line. So we say that y is equal to mx plus c plus error, and that error has to be minimized. Now once we have this equation, we can have any input to the x. So we have now y is equal to, now I'll write this in form of our analytics equation, but the meaning will still remain the same: beta naught plus beta 1 x plus some irreducible error. Now here, this is your mx, which you have studied in your school, and this is your c, slope and your intercept. So similarly, I'll get some values. Once I have the value for beta naught and beta 1, I can ignore this. Now whatever value I feed for x, I will get the value of y, and that's how I can predict. Now please listen to this very carefully. Here in this graph, this is only for demonstration. Now what we are trying to do is, we are trying to predict the value for y when x is equal to 7. But you have to be very careful about this. You should never ever predict any value outside this range for which you already have some data. We are only doing this for clarity because we did not want it to be in the middle of here. So otherwise it create a mess in the graph. So otherwise you should never extrapolate this until and unless you implement some specific statistical techniques. When you're using basic regression, you should never ever predict some value which is beyond the maximum value in your training data set. Ideally, you should always predict the values between this range. But any which way, as an example, we are saying that if x is 7, then putting the value of x in this equation, I will get maybe 123, right? Based on this beta naught and beta 1. And this is how you can predict any value for y when you have x is known. Now this is simple linear regression because I just have two variables here. However, in reality, I'll have a lot of variables, and all those will, if there are 3 variables in total where I have 2 x variables or 2 independent variables, then my equation will be beta naught plus beta 1 x1 plus beta 2 x2. So the beauty of this is that if you increase the number of x's, the equation still remains the same in terms of its form. You just keep on adding the coefficients and the x's. Now pictorially you can only represent 3 dimensions, as you know. Beyond that you can only do it mathematically, but it is a very generalized model where you can add as many variables as you want. Now as obvious it looks, both these variables y and x have to be numerical because you are using a mathematical equation here. If you have some categorical variables, you cannot use this, or either you have to drop those variables, or there are techniques to convert those variables into numbers, and then eventually you have to read them very different. So once you get into linear regression detail, you will know all of that. But this is some introduction which I wanted to give you right now. So let us move to logistic regression. Now, I told you that in linear regression, the requirement is that both x and y have to be continuous variables, which means they have to be numbers. Sometimes we have to do things where we have classification to do, which means your y-axis or your y variable or your target variable is not a continuous variable, right? It is name of a class. For example, in the beginning, I told you that we need to issue credit cards to good customers only. So you will be having 2 kinds of customers, good and bad, which can be represented in any way, right? You can call them good and bad, you can call them 0 and 1, you can call them approved or rejected, and whatever. These variables will not be continuous. You have discrete or categorical variables. In these kind of situations, when we are trying to map your X variables to the classes, we are doing classification, and here we cannot use these kind of models, right? So we have different set of models which are called classification models, in which your dependent variable is a categorical variable. Now, even though we are talking about only two classes, there can be multiple classes, right? There can be different profiling for customers based on their attributes. So there can be a low spend customers, medium spend customers, average spending customers, and high spending customers. So there can be 4 classes. Now, most of your classification models can be used for either binary classification with 2 classes or multinomial. Logistic regression is also can be used for both binary as well as multinomial. Now, if it is a classification problem or classification model, why do we call it logistic regression? Why are we still calling it regression, right? It's an interesting question which should come to your mind. So let me first explain what logistic regression is, and then maybe I'll tell you why we still call it regression, even though it's a classification model. So this I already explained to you that we have now categories. And here we are taking example of binary format, right? We are not talking about multinomial. We have either yes or no, true or false, high and low, 0 or 1, good or bad, things like those. So this is our class, or this is the value of the Y variable or the dependent variable which we are trying to predict. Now we may have say 20 independent variables which are the values in our historic data based on which we want to predict which class this specific row will fall into. So we will go back, we'll look at the historic data which we'll see, and we will identify based on some modeling techniques to find relationship between this class and those variables. Now again, when we are talking about logistic, the requirement is that your independent variables still have to be continuous, okay? And this will be one of the attributes when I'll tell you why we call it regression. So what we are saying is, if we have only 2 values, let us pick 0 and 1 because that's how we are eventually going to use them. So if I look at this chart and I say on my x-axis, I can have any value, but on y-axis, I have only 2 classes, which is 0 and 1. Here I cannot use a linear regression because the line can go below 0 or more than 1. But why can't we still use the line? Because here the y variable is not a continuous variable. So we cannot use the actual value of the y in that equation, even though we still use the same equation. So let me write that down here. And I'm sure after this, you will understand what we are doing. Beta naught plus beta 1 x1, and this time I'm also going to take more x variable, beta 2 x2 plus so on. Okay, there can be more x variables, so we'll have those many parameters here. Now here I told you your x variable still are continuous variables because that is what we are trying to calculate. However, this y, depending on your x variables and beta naught, beta 1, beta 2, etc., can take any value from minus infinity to plus infinity. And we can't live with that because right now we want our y to be either 0 or 1. So rather than looking at this point value, we convert this problem into something called likelihood problem, or you have studied the probability, right? So now we are talking about the probability. So rather than predicting the actual value, we try to predict the probabilities. And as you know, the probability of anything can never be less than 0 and can never be greater than 1. So this output, so we have to convert this mathematical equation into something else so that the value always stays between 0 and 1. Because what I'm saying is the output which we are going to get, we will be getting the probability of something rather than the actual value. And the probability can never be less than 0 and can never be greater than 1. So it has to lie between 0 and 1. For this, let's first intuitively see what we do. So now what we need to do is, rather than a straight line, we need to derive a function which gives us a value which never goes below 0, never goes beyond 1, always stays here. So if my x is minus infinity, it should just give me y as 0. And then for specific x values, it should give me something between 0 and 1. And after a certain value of x till positive infinite or positive infinity, it should still give me 1. This is where we get the logistic or logit models, a mathematic model, right? And even though we are still using your same regression equation, that is why we still call it logistic regression. So what we do is, before I get into that function, this, rather than getting this edges here, we have, mathematicians have a lot of functions. One of them is sigmoid, which is called a S curve. So it follows what I told you. It ranges from 0 to 1. And rather than a straight line, it's a little curve, but the values always remain between 0 and 1. This is the graphical representation of the mathematical function we use for logistic regression. And what we are looking at now is the y values are probabilities. So what we say is, whenever you input some x values, based on which, on the regression equation which we learned earlier, and playing with that a little to convert it into this sigmoid function, we will get a value between 0 and 1. Now, what will this 0 and 1 represent? These will be probability. So it can be any value, right? You can get 0 0.10, 0 0.19, 0 0.89, 0 0.99, or 1. You will say that if the probability is less than 0.5, you will put that into one class. And if the probability is equal to or greater than 0.5, you will put that row into the other class. And that's how, still using a mathematical equation, we are trying to solve for this. And this is what we are doing. So here, the last component in this equation, 1 divided by 1 plus e to the power minus y, is what is the probability which we are going to get. E, as you might know, that this is the base of natural algorithm. This is, and its value is close to 2.718. And your y here is the same y which was used in the linear regression, which is equal to beta naught plus beta 1 x1 plus beta 2 x2, beta 3 x, and so on and so forth. So internally, first it calculates the value of y, then it gets fed into this formula. And if your y is approaching positive infinity, which means if you replace y with infinity here, you'll get 1 divided by 1 plus e to the power minus infinity, right? Which becomes 0. So this will be 1 divided by 1 equal to 1. So if your y is infinity, you are going to get 1 as your probability. If your y is minus infinity, then this itself becomes infinite, and it becomes 1 divided by infinite equal to 0. So no matter what value you get for y, your outcome will always lie between 0 and 1. So linear versus logistic, we'll just quickly summarize. I told you, in linear regression, we have a continuous variable as your output variable. And in logistic, we have categorical. It solves regression problems. Classification problems are solved by logistic regression. This is denoted by a straight line equation. And this is S curve. Behind the scenes, we are still using straight line, but then we are looking at probabilities and likelihood. That's why we call it a logistic regression, even though it's a classification problem. Sometimes people ask this question in interviews, so you know this now. With that, we kind of now build some fundamentals and foundation on the conceptual knowledge. Now let's see how do we implement this, okay? So let us now look at some code. And as I was telling you, this is based on a research project that we were doing. During this COVID situation, we were trying to look at whether people quit their jobs in IT companies due to techno stress. As you know, with the situation currently, we are using a lot of technology to work from home, and it has both positive and negative impact. And on psychology, from psychology basis, it can create a lot of stress because due to a lot of variables like privacy invasion, no work-life balance, long working hours, and things like those. So I picked this example because it is a very good situation when you have a very generic business problem, and then you have to think very logically and try to identify the variable. This is a typical problem where the business will never know which data they should use. So you have to be very intelligent and smart to identify what data you need, how to select that data, which source systems look at, and things like those, right? Another thing is, we will also talk about data cleaning here, even though we have clean data here because it's based on primary research based on the questionnaire, but then we have a lot of things to do here. We have to convert categorical variables into numerical variables. We have to clean something. We have to fill the missing values and things like that. So it will give you good perspective. Only thing is, it is not a very large data set because, as I told you, this research was done based on primary data collection. So we spoke to employees, we collected the data, and I have to mask this data because this is real research. So I have taken a subset of the data. So here we have, not very large data set, but it will give you good insights on how do we follow the life cycle. And I would assume that you know a little bit of Python. If not, then try to at least understand the concepts. Because the interesting part about these languages, whether it's R, C, or Python, is that to do the same thing, there are multiple ways available because there are a lot of libraries, a lot of functions. So I'm using one of the methods. You might know a different method, or you might see a different method somewhere. So it doesn't really matter. You don't have to remember everything, but it is always good to know that what kind of functions and kind of capabilities are available in a tool. So if you know Python, it's very good. You'll be able to quickly understand. If not, just don't focus too much on the syntax, etc. Try to get the insights and try to get the logic what we are trying to do, and you would know what all is available in this tool to do. Even though it's a very small subset, it's a very large collection of libraries and functions. So let's get right into this. So here I am using data set. Let me also show you the data set here. So after the data was collected, we have already done a lot of processing, and we have kind of calculated some of the variables. So there were like 30 different columns in this data set, and then we have to calculate and create these variables based on those. So that is not part of analytics, but that was one of the processes in data pre-processing. So this turnover is the class where 0 means the employee is not quitting due to techno stress, and 1 is when they are quitting due to techno stress. Then we have some categorical variables here, which are gender, tenure with the company, marital status, family type, and rest all the variables as you see are continuous, right? So these are the actual variables which we are going to use that we have collected the data on. So we are importing some of the libraries like NumPy, Pandas, which are basic libraries built in C language, which gives very efficient way of doing algebraic calculations. And then Pandas is for managing your tabular data as data frames, which internally is built on NumPy itself. Matplotlib is one of the libraries along with Seaborn, which is used for basic graphical representation. Now we are using the read CSV formula or the function of Pandas library to read this data in. So now data, the name is for data frame. If I have to look at the head of the data, which by default gives us 5 rows, I'm seeing that I'm able to retrieve that data here. So I'm getting all this information in my data frame. Then you can always check, what is the number of rows, etc. So I have 111 rows in my data set with 12 columns. So as I was telling you, it's not a large data set, but a very good data set to understand and see how it works. Now, if I have to look at some basic information so that I know what all variables I need to work with in terms of pre-processing and cleaning, etc. So I can use the info function on my data frame. So I say data.info. It shows me all my columns. And then all these are very important fields, which is first is non-null count, which means how many rows are there for this column, which are non-null. So if you see, all of my rows are equal to 111, which is the total number of rows in my data set. But one is 106, which is age. So I know there are 5 values missing. Now, once the first thing which I am looking at is any missing values, right? After my data type and everything is fine, and I manually, looked at different columns, and I'm comfortable with my data set. Now what I'm seeing is, are there any missing values? So how do we deal with this situation? Now, if I know there are some missing values, if there was a situation where I had, say, hundreds and thousands of rows and just a handful of values are missing, and I want to save my time on the project and I don't want to spend too much time on this, I can delete those rows because they are like 0.001% of my data set, so it doesn't make much of a difference. However, generally that doesn't happen. There will be a significant values would be missing from your data set. If they are, for example, here 5 out of 150, 111 is a big deal, right? I don't want to miss because all other columns are filled for all those 5 rows as well. So I don't want to miss the information on the other columns just due to one column. So what I'll try to do is I'll try to assume some value, which is not assumption, but it is based on some statistics measures, where I will try to put some values in those 5 rows for age. Now there can be different ways, and it is always contextual, as I told you earlier. Generally here what I'm seeing is it's age column, so the ages would range, of employees will always be, say, between 22, 23 to say 60. So if I kind of take an average of those ages and put that in the missing values, my overall predictions, etc., are not going to change, right? If you understand it from statistical perspective. If it was a categorical variable, for example, I would look at, again, the central tendency from statistics, and I look at the mod, like which is the most common occurring category, and I'll put that. Even though that might change it a little, but still I'm going to save a lot of information. The rest 10 variables are still saved. Sometimes what we do is we will run another regression model or classification model, assuming now age is my dependent variable. I'll take all the other variables as an independent variable, and I run a regression model and treat these 5 rows as my production data, and I'll try to predict the age based on the model trained on the rest of 106 rows, right? So there can be different ways you do this based on the context you are in, but it is very important to fill the missing values. Another thing I'm seeing here is there are a lot of categorical variables which are represented by object data type. And int 64 and float 64, these are of course integers or real numbers where we are having numbers. So we are good, but we need to convert others into some numeric values. And there's a concept of dummy variables. So if there are n categories in a column, for example, gender has 2 categories, you will be building n-1 new column. So here it will have just 1 column created for gender. However, for tenure, if there are, say, 4 different tenures, less than 3 years, between 3 to 5, more than 5, and things like those, it will create 3 new columns with giving value of ones and zeros. Now, it's another concept. So I think you should spend time on understanding what are dummy variables and how do we use them. But here, what I'm trying to do is I'm converting all my categorical variables into numeric variables using the pandas function getDummies. Drop first is true, which means within this code, what I'm doing is I'm taking this data set, which is called data. I am converting all my categorical values into dummy variables, and I'm also dropping my categorical variable so that and putting again in the same data set. Let us run this again. So now if you see, I have all the variables converted into numeric, and it has different number of variables. For example, I was telling you that for gender, it will just create 1 variable, 1 column, because I have only 2 categories. For tenure, I think there were 4 categories, so it has created 3. Now, whenever I have 1 in the row of gender male, it means in the real data, this value was male, and then there was a female here. That's why in this male column, I have a 0. So I will not get into much details on this right now, but you can go through and understand more about dummy variables because it's important. Then I am now feeding my, so let's see what is the average age. It's like 31.15 years. Now what I do is I feed or fill the missing values using fill NA function in my data age column, right? And I'm doing that using mean values. So I do that. Now if I run data info, I see all my variables are non-object, which is non-categorical. All are numeric, and there are no missing values now because I have a non-null count as 111, right? So my basic pre-processing happens like this. Once you are completely sure that you have no missing values, you have treated outliers, and you do a lot of other things, then you can move to exploratory data analysis, where you try to understand the basic patterns. So here we are using the C1 library to build some basic charts. Now what I'm looking at is turnover. So I see these are 2 balanced classes, right? We have almost equal number of objects in 0 and 1, whether somebody has resigned or not. So that gives us some confidence on our data. Then we are looking at, is there a relationship between gender and turnover? So I see that there are more males in my data set than females. So overall, I see that there are lesser females and more males. But if I look at comparing the gender within the class, I see the turnover 0 means they have not resigned. So I see that lesser females are resigning due to techno stress, more males are resigning due to techno stress. So this can be a very interesting hypothesis, right? So you will draw a lot of charts between different variables, etc. But this is how it will give you some direction in terms of what you're trying to test. Then what I do is I remove this turnover column from my data set because I want to train without this. And I will also create another data set called Y. So I'm creating two different data sets now. If you know Python, you know in the sklearn, which is scikit library, we have a function called train test split. What we do is we split our data into different sets. For example, you like to test your model with some data which has not seen. So we call that as test data or validation data. And we use primary data set for our training. So I'm calling that function. And when I use this function train test split on my tables X and Y, and I'm saying test size is 0.3, which means 30% of data is reserved for testing. By default, it gives me 4 different data sets. So I can call them anything. So here, these are the variable names. So it will automatically divide my data into 4 data sets, X variables and Y. And within X and Y, I have training and test. So 70% of data will go into X train and Y train, and 30% of data will go into X test and Y test. And obviously, X train and X test only contain your independent variable, and Y train and Y test containing a dependent variable. Now I am running logistic regression again using from scikit-learn from a linear model sublibrary. I basically bring this model, and here I am putting the outcome into my variable called log model, on which I will be training this data set. So here I am just showing you the head, which is the 70% of the data without my turnover column. Now what I do is I train my model on the training data set X train and Y train. So once I do that, it is going to show me what all parameters by default it is using. The only parameter I changed was maximum iterations. This data being very small, if I run it on lesser iterations, it might not work. So let us test that quickly. And if I run this, okay, on 100 it is running fine. See, for 50 iteration it failed because it's a smaller data set. So it will also need a lot of information to train, right? So larger the data set, better it is. So here I'm just saying run more iterations and do more calculations, etc. And then there are a lot of other attributes here. I'll just talk about, say, the first one, see, the concept of overfitting, where the training data set kind of creates a bias in your model. It works very well on training, shows good accuracy, but when you move to production and if there's a change in the data, it starts to behave very poorly. So there is a parameter called inverse of regularization, which is this C value, which takes care of if you increase the parameters to very high values. For example, if I do iterations to 1000, this will start to penalize this model and will lower down the accuracy. Then of course there are something to do with penalization, how much do I penalize, and things like those. So there are a lot of parameters in this function which by default are standardized. It also talks about whether I'm talking about, for example, solver LBFGS means I'm doing binary classification, right? I told you we can do a multinomial classification as well. Then it also can help you to change your threshold values. By default, it's 0.50. So whenever you have 0.50, it is probability till 0.50, it will have one class, otherwise it will have the other class. So now what I do is I take my test data and predict. And for that, I will create a confusion matrix and the outcome of confusion. Let me just quickly run this. So now what it tells is that once you run this model on test data, your accuracy of your model is coming out to be 91%. Now, even though it looks very good, like accuracy of 91% sounds very interesting, but there are some other parameters or attributes which you need to check, because sometimes accuracy alone is not a very good parameter. For example, you are trying to predict some fraudulent transactions. Now, out of 100,000 transactions, there may be just 20 fraudulent transactions. If you train a model and you say every transaction is non-fraudulent, you are actually only predicting 20 wrong rows. So your accuracy will be 99.9%, even though accuracy is 99.9%, but your model is completely useless, because if it is not identifying any fraudulent transaction, it is of no use. For that, you have to use 2 other measures, which are precision and recall, which is also given in your confusion matrix when you run this. So I have shown you a picture here. How do we calculate that? So true positive is 18 here, which means out of overall 20 correct values, you are able to identify 18 as correct and 13 as correct other class, which is your true negative. But then there are 3 predictions which you have done wrongly. Now these are called false positive and false negative. So your recall is nothing but is also called your sensitivity, which is true positive divided by true positive plus false negative, which means you are saying 18 divided by 19, which will come around 95%, which is your recall here, 95%. What does it mean? It means that out of all the true positives you have done, how many of them are actually correct? Out of 19, how many are correctly predicted? So you are saying you are predicting 95%. On your precision, which means true positive divided by true positive plus false positive. So the denominator represents all the true positives, actually which were positive, but you have also predicted only some of them. So when you are talking about the precision, you are saying that out of the actual true values, how many were you able to identify? If precision, recall, and your accuracy are close to each other, then your model is doing very good in both the positive and negative predictions. If there is a huge difference between accuracy and one of the measures between precision and recall, like the example which I told you, in that your accuracy will be 99%, your precision will be 99%, but your recall will be 0, which will tell you that your model is not good. So whenever you are doing classification, you will always use a confusion matrix, and you will always focus on these three parameters. They should be as close to each other as possible, as well as high as possible. So thank you so much for attending. Bye bye.